I really like this quote. Elements vary widely in their properties, but in an orderly way. That's from a textbook by Holt. Um, they really do, and that's the amazing thing, and the thing that made Dmitry Mendeleev a pioneer and able to start putting together the periodic table as we know it. Today we're going to talk about physical properties and the periodic trends. So some of those groupings that we had. So a trend is a predictable change in a particular direction. And the purpose of looking at trends is to make logical predictions about element behavior. So one of our trends, or one of our physical properties that we look at, are the atomic radii. And it's the atom size as determined by how far the electrons are from the nucleus. And the definition of it is the distance between the nuclei of two identical atoms divided by 2. This is if we can get them actually to bond, and these would be ideal for our diatomic molecules. And it really just helps us because we know the electrons are always in motion and impossible to identify the specific location at a specific time. So pinpointing that radius just with one atom is not doable with our normal things. But if we have two of the same atom combined and we look at where their nucleuses are and divide that by 2, we're able to figure out what that radius would be. So as we go from left to right, the radius gets smaller. So as we're going across a period from left to right, so if we're looking at the lithium period, lithium, beryllium, boron, carbon, nitrogen, oxygen, over to fluorine, we're getting smaller as we go across. And that's because the electrons are all in the same energy level. We know that that's the first energy level if we're looking at that row. And we just keep adding to that, and we keep adding protons to the nucleus. So we have it so that we're slowly pulling those together, and we know that we have a more powerful magnet, basically, with the positive side and the negative side of the magnet. It's going to pull more towards one another than a weak magnet. So that's the same sort of thing that's happening here. The nucleus, we're adding more and more protons to. That first energy or second energy level, we're adding more and more electrons to. Those positives and negatives are going to be pulling one another even closer. As we go from top to bottom, so we're looking at one of the columns or one of the families, we're getting bigger. And that's because we're adding another energy level as we go from one period to the next. So if I look at the alkali metals, lithium to sodium, sodium's going to be bigger because I'm adding that extra energy level, so I'm going out further from the nucleus. I'm into the third energy level now, so I'm further from the nucleus. And those inner electrons are going to act in a way that they shield the outer electrons from the full charge of the nucleus. So I'm still adding protons to the nucleus, but I have electrons in between that are kind of shielding me from seeing it. It's kind of like going to a concert where the nucleus is that band that you really wanted to see, but you've got a whole bunch of people in front of you because you couldn't get front row seats. The further out you go, the more difficulty you'll have seeing the band that you paid the big money to go see. So it's shielding you from seeing that concert to the full capabilities of that concert. Same sort of thing. The electrons that are in the way are shielding the effects of those protons that we're adding to the nucleus, and that is just called the shielding effect. So here's a little summary for you. Got our periodic table there. We're getting smaller as we go left to right, bigger as we go top to bottom. So let's look here. Which of the element pairs would have the larger atomic radii? Bromine or chlorine? Chlorine we know is above bromine, so that's going to be smaller than bromine, which would be bigger. It's down lower. And zirconium or niobium, I don't have a periodic table in front of me. Give that one a try, though, and see what you can figure out. You won't have ones examples where they're diagonal, because that just wouldn't be fair without actual data. It's always going to be in a row or in a column, so it's easy for you to determine based off of those rules. Okay, we do have some exceptions. The noble gases are an exception to this general periodic table rule because they have that full outer energy level, and the electrons are not interacting with other atoms. So X-ray diffraction doesn't work to make the measurements, so we don't have actual clear data for use with this. Ionic radius is slightly different from our regular radius. It's the radius of an ion. So after a metal has lost an electron, or after a non-metal has gained an electron, what's going to happen to their radii? Well, positive ions are going to become smaller than their parent atoms, and so we can think of that metal there. Let's think of lithium. Lithium is an alkali metal. It's in the first column, so we learned that that means that it has, for whatever energy level it is, S1. Well, it'll lose that one valence electron to become like one of the noble gases in its electron configuration. That makes it positive because it has one less proton than it did before, which we call a cation. And so we think of that, it has lost what was in its outermost energy level, so clearly it's going to be smaller than it was before. The negative ions, which come from our nonmetals, we call them anions, they've gained electrons to become like their nearest noble gas. And since they're gaining electrons, they're becoming more negative, and they are larger than their parent atoms because they are going to be repelling the other electrons that are around them more, and we're not adding more protons, so there's not more protons to pull those electrons in even more. So here's some what we call an isoelectronic series. All of these have 10 electrons, and that's, we can see in the electron configurations here. They all have those 10, and they come from, like oxygen has lost 2, fluorine has lost 1, neon is just that normal stable 10, sodium had lost 1, and magnesium had lost 1. And so as we're getting bigger. We gain just 1, so we're only slightly bigger. Neon is just stable. But sodium lost 1, so it's becoming smaller, and magnesium lost 1, so it's becoming smaller. Okay, our next trend is the ionization energy. And the definition of this is the energy required to remove an electron from an atom. So if an atom we know is neutral, to become a positive ion, it has to lose an electron. And there has to be some energy put in to remove that electron. And this is how we figure out, is it easy for it to lose that electron, or is it difficult for it to lose that electron? We can think the metals, we know it's going to be easy to lose that electron, so it doesn't require much energy. If we wanted to remove an electron from a nonmetal, which are so much closer to the noble gases if they gain an electron, that it's going to be much more difficult to lose that electron, and therefore it would require more energy. So the energy required to remove an electron from a given element is a constant for that element, and a unique property as well. As we go left to right, the ionization energy gets bigger. It increases because we need more energy to remove or take out an electron. As we go to the right, the atoms want to gain electrons, not lose them. As we go from the top of the periodic table to the bottom in a column, we get a smaller ionization energy. It's easier to remove electrons. So less energy is required to remove an electron as we go down a column. And that's, again, due to that shielding effect that we saw with the radius. So as the radius is increasing, because of the shielding effect, the ionization energy is decreasing because those inner electrons are blocking the attraction of the protons to the outer electrons. Therefore, they're held less tightly, and not as much energy would be required to remove it. So here's our summary. It's just the opposite of the atomic radii trend. So as we go from left to right, it's harder to remove those electrons, so the ionization energy is bigger. And as we go top to bottom, the shielding effect is having the opposite effect. It's decreasing the amount of energy that is required to make it an ion. Okay, electronegativity is how strongly an atom attracts electrons of other atoms to itself, which is closely related to the ionization energy. So, as we go from left to right, our electronegativity becomes bigger, and as we go top to bottom, our electronegativity becomes smaller. It's harder for those like francium to pull electrons from another element to itself because it's so lightly holding its own electrons to itself due to that shielding effect. Okay, make sure to read through the textbook and about those trends in melting and boiling points.